A silent stone giant weighs more than 10 elephants. The moai of Easter Island are among history's most baffling creations, carved and moved by a people with no metal, no wheels, and no large animals. By the end of this journey, you will understand the precise engineering logic that made these impossible figures possible. How did a society move multi-ton statues for miles across rugged terrain? And what brilliant trick allowed them to stand these giants upright? We are about to decode a marvel of physics and human ingenuity that reshapes what we think ancient cultures could achieve. What does true innovation look like when you have nothing but stone, rope, and determination? Rapa is the heart of the mystery. This dormant volcano is not just a location, it is the very source. Its slopes are made of a unique volcanic rock called tuff, which is essentially ancient volcanic ash that settled and solidified over millennia. To the modern eye, it looks like solid stone, but to the ancient Rapa Nui carvers, it was the perfect medium. Freshly quarried from the moist interior of the crater, this tuff is surprisingly soft, almost like a hard chalk. A master carver could shape it with stone tools made of basalt, a much harder volcanic rock found elsewhere on the island. They would use these basalt picks, called toki, to chip and pound away at the soft tuff, gradually releasing the giant form trapped within the mountain. But here is the first brilliant piece of engineering logic. Once this carved tuff is exposed to the open air, it begins to dry and harden significantly. The islanders were not just sculptors, they were material scientists working with a self-curing stone. They chose a material that was easy to work with during creation, but would become durable and resilient for its final journey and eternal vigil. The quarry face at Rapa is perhaps the most evocative archaeological site on Earth. It is a workshop abruptly paused. Nearly 400 moai are scattered across its slopes in every conceivable stage of completion. Some are mere outlines, just the suggestion of a brow and a nose emerging from the bedrock. Others are fully carved on the front and sides, but remain attached to the mountain by a thin spine of rock along their back, like a figure halfway out of a stone womb. A few lie finished and prone, as if waiting for the signal to begin their trek. This frozen moment gives us a complete instruction manual. We can see exactly how they were made, from the initial outline to the final polishing. The carvers worked with an intimate understanding of the stone's grain and structure, carving in a way that followed its natural weaknesses to prevent catastrophic cracks. This deep, generations-old knowledge of their single most important resource was the foundational engineering principle. Before a single statue could be moved an inch, the Rapa Nui had already solved the problem of creation by selecting and mastering the perfect geological canvas. This top-down approach to carving is a complete inversion of how we would likely tackle the problem today. Our modern instinct is to quarry a block, transport it to a workshop, and then begin the careful work of sculpting. But the Rapa Nui masters understood their material and their limitations on a profound level. By carving the statue directly into the living rock of the quarry wall, they solved multiple critical engineering challenges at once. The first and most important was stability. As they meticulously chiseled the details of a stern brow, a long nose, or pursed lips, the entire multi-ton mass of the statue remained securely anchored to the mountain. There was no danger of it tipping over during the delicate final stages of work. This method also provided natural scaffolding. The carvers could stand on the surrounding bedrock or on platforms built against the cliff face, giving them direct access to every part of the emerging giant from head to toe. The final connection to the mountain was a narrow keel of stone left along the statue's back. It acted like a built-in support beam, holding the figure in place until the community was absolutely ready for the next, most daring phase of the operation. Only when the carving was complete and the statue was polished smooth would this keel be carefully broken, allowing the moai to be gently lowered onto the quarry slope in a controlled descent. This entire process speaks to a patient, deliberate engineering philosophy. It was not about speed, it was about absolute control. Every decision was made to eliminate unnecessary risk when working with such precious and massive objects. They turned the mountain itself into the ultimate tool, a solid, immovable vise that held their masterpiece securely until the very last moment. This final severance was a masterpiece of applied physics. After months or years of careful shaping, the moai was attached to the mountain by just that single, narrow spine of stone along its back. To break this connection, the Rapa Nui engineers could not simply swing a heavy hammer. A direct blow could send shockwaves through the entire statue, creating hidden fractures that might cause it to shatter later. Instead, they likely employed a method of controlled tension. One compelling theory suggests they used simple wooden wedges. Workers would have carved narrow slots into the keel, tapping dry wedges of tough local wood into place. Then they would pour seawater over the wedges. As the wood absorbed the moisture, it would expand with tremendous, gradual force. This slow, even pressure would coax a clean fracture along a predetermined line, allowing the keel to snap without violently jarring the statue itself. It was a process of persuasion, not brute force. With the keel broken, the multi-ton giant was now free, but it was also precariously perched on a steep quarry slope. Lowering it safely to the ground was the next critical operation. Archaeologists have found evidence of prepared ramps and embankments at the base of Rapa. It is likely the statue was guided down using a combination of rope cables made from braided tree bark and a series of wooden levers. Teams would have carefully controlled the descent, letting gravity do the work while they managed the speed, perhaps sliding the moai on a lubricated track of mud or crushed vegetation. The moment it settled onto its prepared bed of stones was a triumph. The statue had survived its first and most vulnerable transition, moving from a fixed part of the landscape to a sovereign object. This successful separation proved its structural integrity. It was now ready for the greatest challenge of all, the journey across the island to its permanent home. The moment the moai lay horizontal on the quarry slope presented the ultimate engineering puzzle. How do you move a 70-ton stone giant across miles of undulating, rocky terrain without wheels, without beasts of burden, and without modern machinery? For decades, the accepted answer was a slow, grinding drag. The conventional theory held that the Rapa Nui laid the statues on log sledges or wooden frames and painstakingly pulled them along lubricated tracks, a method that seemed logical but came with immense practical difficulties, requiring vast amounts of timber and an almost unimaginable amount of coordinated labor. But what if the solution was not to drag the moai but to make it move itself? This leads us to the second revolutionary principle of their engineering logic, a dynamic pivot that transforms our understanding of ancient innovation. Archaeologists Terry Hunt and Carl Lipo proposed a theory so elegant it seems almost like magic. They suggested the statues were not dragged at all, but were walked upright to their coastal platforms. The concept hinges on the moai's distinctive design. Most of the giants have a pronounced, rounded belly that tapers down to a narrow, curved base. This is not just an artistic choice, it is a critical engineering feature. Imagine two teams with sturdy ropes made from braided tree bark. One rope is tied high on the statue's front, another on its back. The crews pull rhythmically, not with a constant strain, but with a coordinated rocking motion. As the team in front pulls, the statue tilts forward, pivoting on its curved belly. Before it can tip over, that team relaxes and the crew in the back pulls, rocking the giant back and then forward again onto a new point of its base. With each controlled sway, the statue takes a step. This method leverages the statue's own immense weight and center of gravity, converting its monolithic form into a controlled, oscillating pendulum. The physics are beautiful in their simplicity. The curved base acts as a natural rocker, and the rhythmic pulling creates a walking gait. Experiments with full-scale concrete replicas have proven it is not only possible but remarkably efficient. A crew of just 18 people was able to walk a multi-ton replica hundreds of yards in a matter of minutes. This turns the conventional logic completely on its head. Instead of fighting the statue's weight with brute force, the Rapa Nui engineers collaborated with it, using physics to coax the giant into a slow, dignified procession across the land. It was a ceremony in motion, a literal walking of the ancestors that required not just muscle, but precise rhythm, communication, and a deep, intuitive understanding of balance. The journey itself became a powerful communal act, a display of harmony between the people, their leaders, and the very laws of the physical world. The walking theory reveals a brilliant collaboration with physics, but it is not the only possible answer. Another compelling piece of the puzzle relies on a more grounded, yet equally ingenious form of engineering logic. This third principle focuses on friction reduction, the ancient science of making heavy things slide. Imagine laying the finished moai prone on a sturdy wooden sledge, a cradle built from the island's tall palm trees. The statue is securely lashed to this frame, and the entire assembly is placed upon a prepared track. But pulling a multi-ton sledge directly over dirt or stone is nearly impossible. The friction is simply too great. The breakthrough came from what they placed on the path itself. Researchers have proposed that the Rapa Nui used rollers, perhaps cut sections of palm trunk, laid perpendicular across the statue's route. The sledge would be pulled over these rolling logs, a method that dramatically reduces the resistive force. Yet even rollers create significant drag. The true masterstroke may have been in the lubrication. Historical accounts and experimental archaeology point to a humble, organic solution: sweet potato paste. By creating a slippery slurry from mashed sweet potatoes and spreading it on the track or directly on the rollers, the islanders engineered a surface with an extremely low coefficient of friction. This simple, locally sourced lubricant transforms the physics of the problem. With a well-lubricated track, the force required to initiate movement plummets. A statue weighing 10 tons might be moved by a coordinated team of several dozen people pulling on strong ropes, rather than an army of hundreds. This approach represents a different kind of genius. It is an applied understanding of tribology, the science of friction, wear, and lubrication, using nothing but natural materials. It speaks to a culture that observed a fundamental constraint of the physical world, the stubborn grip between surfaces, and devised an elegant, edible answer. Whether the statues walked or were pulled on greased tracks, the core logic is the same: identify the primary force opposing you and innovate a way to minimize it with the resources at hand. The roads of Easter Island are a testament to foresight. These ancient transport corridors, radiating from the quarry at Rapa toward the distant coasts, are far more than worn footpaths. They are a permanent, engineered landscape, a massive infrastructure project carved into the island's volcanic skin. To move a 70-ton statue, you cannot simply choose the shortest line between 2 points. You must sculpt the very earth to serve your purpose. The logic behind these roads is brilliantly pragmatic. Surveyors and builders first identified the most feasible routes, avoiding the steepest ravines and most treacherous rock fields. They then physically modified the terrain, creating a cleared, leveled track often bordered by raised earthen margins or lines of stones. These borders were not decorative. They acted as guide rails, ensuring the statue or its sledge stayed on course during the delicate inch-by-inch procession. The roads were also graded with a gentle, consistent slope wherever possible, a clear indication that the builders understood the limits of human and material endurance. An incline too steep would make the statue impossible to control, while a decline too sharp could turn it into a runaway boulder. Every contour of the path was a calculated decision in the grand equation of movement. But the true engineering genius of these roads is revealed at their most challenging points, the turns. A straight path is one thing, but how do you pivot a multi-story stone giant to navigate around an outcrop or change direction toward its final platform? The answer lies in prepared pivot points. Archaeologists have identified wide, circular areas along these ancient roads, often paved with flat stones. These are not resting places, they are rotational platforms. Imagine the statue, whether being walked or pulled on a sledge, being carefully maneuvered into the center of such a circle. Using long wooden levers inserted beneath its base or frame, and with teams pulling on strategic ropes, the crews could incrementally swing the entire mass around a central point, like turning a colossal key in a stone lock. This process of reorientation required immense coordination and control, turning a potentially disastrous maneuver into a slow, methodical dance. These pivot points transform our understanding of the operation from a simple haul into a sophisticated logistical sequence with predefined stations for specific, complex actions. The roads and their features represent a long-term communal investment, a landscape-scale tool that outlived any single project. They show a society thinking not in seasons, but in generations, permanently reshaping their world to serve a vision that connected the mountain of creation to the shores of their ancestors. Every step of the journey was a negotiation with an invisible point. Deep within the form of each moai, whether lying flat on a sledge or swaying upright on its walk, existed its center of gravity. This is not a mystical concept, but a very physical one, the precise point where an object's mass is perfectly balanced. For the Rapa Nui engineers, managing this point was the fourth and most critical principle, an unspoken law that governed every decision from the quarry to the coast. Their entire operation was a continuous, real-time experiment in statics, the branch of physics dealing with objects at rest or in equilibrium. They could not afford a single major miscalculation. Consider the statue's iconic design. The massive, rounded head and broad shoulders might seem top-heavy, but the sculptors cleverly compensated with an even more massive, protruding belly and a torso that tapered to a relatively narrow base. This deliberate proportioning placed the statue's center of mass surprisingly low, down in the abdominal region. For the walking method, this low center was a gift. When the teams rocked the statue forward, that heavy belly acted as a pendulum weight, helping to control the sway and making it easier to pivot the giant onto a new point of contact. The curved base was the pivot, but the low center of gravity was the anchor that kept the entire motion from devolving into a catastrophic topple. It was a dynamic stability earned through form. For prone transport, the challenge was different but rooted in the same physics. A statue lashed to a sledge is a potential disaster waiting for a slope. If its center of mass is too high, or if the lashings are uneven, the entire load can shift, roll, or even crush the pulling teams. The solution was in the securement. The Rapa Nui likely used a system of strong, fibrous ropes in a crisscrossing web, lashing the statue not just at the top, but at multiple strategic points to distribute force and lock the mass firmly to its wooden cradle. They were, in essence, creating a single, unified object sledge and statue together, with a combined center of gravity that was low, centered, and predictable. This hands-on knowledge was not written in any manual. It was learned through generations of observation, through stories of both triumph and heartbreaking loss when a statue fell. It was a cultural inheritance of practical physics, where the penalty for error was the destruction of a community's years of sacred labor. This intuitive mastery of balance and mass is what transformed an impossible dream into a repeatable process, allowing the silent giants to complete their slow procession toward the sea. The true masterpiece of Easter Island was not carved from tuff, but woven from the community itself. Every physical technique we have explored, from the rocking walk to the lubricated track, depended entirely on a more profound form of engineering, the human engine. To move a 70-ton giant, you need more than rope and levers. You need a symphony of synchronized effort. The most critical infrastructure was not built of wood or stone. It was built of people, organized into a living, breathing machine of astonishing coordination. This social machine required flawless design. Historians estimate that moving a single large moai would have required a coordinated labor force of several hundred individuals. This was not a chaotic mob, but a precisely structured operation with clear leadership, specialized roles, and a chain of command. There would have been master engineers who understood the physics of balance, pathfinders who scouted the route ahead, rope teams of immense strength, lever crews with an eye for precise placement, and support personnel managing supplies, food, and morale. The project management and human resource allocation behind these operations were as sophisticated as any modern construction plan, just encoded in tradition and oral knowledge rather than blueprints. The synchronization of this human machine was its beating heart. Imagine the scene: hundreds of people arrayed along thick bark fiber ropes, their hands gripping the coarse fibers. A single voice, or perhaps a rhythm beaten on a wooden drum, would rise above the crowd. This was not just music, it was a critical control system. A specific chant would signal everyone to take the strain, another to pull, another to hold, and another to release. The rhythmic calls transformed individual muscle into a single, unified force, allowing the teams to pull in perfect unison for the walking method, or to heave together in coordinated bursts to overcome static friction on a sledge. This shared rhythm did more than coordinate muscles, it aligned minds, turning exhausting labor into a shared, purposeful ritual. The social cohesion required for such an undertaking was the ultimate, invisible infrastructure. It speaks to a society with a powerful collective identity and a deep-seated belief in the importance of their shared mission. The act of moving an ancestor became a reaffirmation of community itself, each synchronized pull weaving the people tighter together. The engineering logic here is profoundly sociological, proving that the greatest monuments are not testaments to what people can lift, but to what they can build together. The Ahu stands as the final, defiant answer to gravity. After a journey of miles, the moai reached its sacred stage, a long stone platform built with breathtaking precision right at the ocean's edge. This was not a simple slab, but a monumental feat of dry stone masonry. Master builders fitted together massive blocks of dense basalt, a stone far harder than the tuff of the statues, without any mortar. Each block was carefully shaped so that its weight and the friction of its neighbors locked the entire structure together. The result was a perfectly level, incredibly stable foundation, an artificial cliff designed to bear the colossal weight of the ancestors for centuries. The logic had now shifted completely from dynamic movement to absolute, eternal stasis. Every angle, every joint was calculated to distribute tons of pressure down into the solid earth, preventing any settling or tilting that could topple the giant it was meant to support. But the Ahu was more than a pedestal. It was the last and most critical piece of installation equipment. Its builders often incorporated a defining feature, a sloping ramp of earth and stone built against the inland side of the platform. This ramp was the key to the final, seemingly impossible act, transforming the prone statue from a traveler into a towering sentinel. The prone statue now faced its final and most daunting ascent. After its epic journey, the moai lay at the foot of the Ahu's sloping ramp, its back to the earth, staring blankly at the sky. The challenge was almost incomprehensible: to raise this multi-ton stone giant from a horizontal position to a vertical one, and then to seat it perfectly atop the platform. This is where we encounter the fifth and perhaps most patient principle of their engineering logic: the power of the incremental lift. The prevailing theory for this final act is a masterpiece of simple mechanics, relying on two of humanity's oldest tools, the lever and the inclined plane. Long, sturdy poles of timber, likely from the island's tall palms, were inserted beneath the statue's head. Teams would throw their weight onto the ends of these levers, using the solid ground as a fulcrum. With a coordinated heave, they could lift the massive head just an inch or two. In that fleeting moment, before the lever could slip or the statue settle back, other workers would rush in to pack stones, gravel, and rubble into the newly created space. This was the critical maneuver, a lift and pack. The lever was then reset and the process repeated, lifting the head another inch and packing more material underneath. Each cycle was minuscule, but the cumulative effect was transformative. Over hundreds, perhaps thousands, of these painstaking repetitions, the statue's head end would slowly, incrementally, walk its way up the prepared earthen ramp. The inclined plane of the ramp did its part, converting the vertical lift into a more manageable diagonal push. The statue's own immense weight, once the greatest obstacle, now became an asset, helping to compact the packed stone fill beneath it with each tiny ascent. This method represents a profound understanding of breaking an impossible problem into a series of possible ones. They did not attempt a single, heroic lift, a feat far beyond any human or wooden technology of the time. Instead, they engineered a process that converted a 70-ton lift into thousands of one-pound lifts, spread over days or weeks of meticulous, rhythmic labor. It was the ultimate exercise in patience and systems thinking, a physical algorithm executed with stone, wood, and unwavering determination. The community's rhythm, so vital for the walking phase, now found a slower, more deliberate beat, a chant marking each small, collective victory against gravity. Yet the journey was not always complete with the statue standing tall. For some of the most important moai, a final, crowning touch awaited: a massive cylindrical stone called a pucao. These distinctive topknots, carved from a different quarry of vibrant red volcanic rock, present one last, elegant engineering puzzle. After mastering the movement and erection of the giants themselves, how did the Rapa Nui place a multi-ton stone hat, perfectly balanced, on a head that was already over a dozen feet in the air? The logic here shifts from grand transport to a final, delicate act of precision assembly. The pucao were quarried from Puna Pau, a site known for its unique red scoria, a lighter and more porous stone than the tuff of the main statues. This was a deliberate choice, reducing the weight of this final component, but a pucao could still weigh as much as 2 elephants. Transporting it across the island to the waiting moai was a challenge in itself, likely using the same walking or sledge methods perfected for the statues. But the real ingenuity was in the placement. One compelling theory imagines the community building one last great earthwork. After the moai was securely upright on its ahu, workers would construct a massive earthen ramp directly behind the statue, rising up to meet the height of its head. This ramp would have been a temporary mountain built solely for this final task. The pucao would then be rolled or dragged up this incline, a slow ascent to the pinnacle. Once it reached the top, positioned just behind the moai's head, the delicate operation began. Using ropes and levers, crews would have carefully tipped the cylindrical stone forward, guiding it to pivot and settle onto the statue's flat, prepared pate. It was a controlled fall of immense consequence, requiring millimeter precision to ensure the pucao landed centered and secure. An alternative theory suggests an even more daring technique: a cantilevered lever system. Imagine a tall, sturdy timber frame built beside the statue, with a long horizontal beam projecting out over the moai's head. The pukow could be hoisted using ropes and then swung into position, lowered with painstaking care onto its resting place. Whichever method they used, the final moment of contact required breathtaking calculation. The statue's neck, already supporting the massive head, had to bear an asymmetric, shifting load as the pukow was tilted and settled. A miscalculation in balance could have sent the topknot crashing down, potentially damaging the moai or the platform below. This was not brute force, it was the culmination of all their accumulated knowledge, a final demonstration of patience, coordination, and trust in physics. The successful placement of the pukow was more than an architectural feat. It was the last symbolic act, dressing the ancestor in its full, majestic regalia, a red crown against the blue Pacific sky. The silent giants along the roads tell another story. Scattered across the island's ancient transport corridors, dozens of moai lie where they fell, forever frozen in mid-journey. Others never even left the quarry, their forms half emerged from the volcanic tuff. To see these as mere failures is to miss a crucial piece of the engineering puzzle. These abandoned figures are not evidence of a broken system, but rather its most honest data points. They reveal the immense, ever-present risk that shadowed every operation. The logic was brilliant, but it was not magic. It was a hard-won, empirical science practiced at a monumental scale, where the penalty for a single mistake was absolute. A rope woven from tree bark, stressed beyond its limit by an unexpected jolt, could snap with a sound like thunder. A wooden lever bearing tons of pressure might fracture at a critical moment. Even a slight miscalculation in the rhythmic pull during the walking method, a single team out of sync, could shift the statue's center of gravity past the point of no return. In an instant, a decades-long project could end in catastrophic and irreparable damage. The fallen moai, often cracked or embedded deep into the earth from the force of their impact, were beyond repair. The community faced a heartbreaking but pragmatic decision. They could not recycle the stone. The investment of labor, the sacred purpose of that specific ancestor, was lost. This is the sixth principle, the sobering logic of sunk cost. When a statue fell, the rational choice was to abandon it and begin anew. This reality underscores that their success was never guaranteed. Each completed journey was a victory against staggering odds, a testament not to infallible technique, but to the resilience of a people who learned from every setback. These silent sentinels of failure, resting where they fell, are perhaps the most powerful reminders of the human endeavor behind the mystery. They transform the moai from mythical impossibilities into achievements carved from patience, courage, and an unwavering willingness to try again. But the story of the moai does not end with their physical placement. The seventh principle moves us from the mechanics of movement to the profound meaning of location. Where each giant was placed, and the exact direction of its eternal gaze, was a final, deliberate act of engineering that wove the statues into the very fabric of the island's life and cosmos. This was not random. The builders were not just moving stone, they were mapping meaning onto the landscape with astronomical and geospatial precision. Many of the great Ahu platforms are aligned with celestial events. On the winter solstice, for example, the sun rises directly behind specific platforms, framing the stone giants in a halo of light, a phenomenon that would have marked a pivotal moment in the annual cycle for the watching community. Others face the direction of the summer solstice sunset or key lunar standstills. Achieving this required a deep, generational knowledge of the sky, a living calendar etched not on paper, but in the orientation of multi-ton monuments. The logic also turned horizontally toward the practical necessities of survival. Numerous Ahu and their moai are positioned to face inland, their backs to the sea, gazing directly over the communities they watched over. More than just symbolic guardianship, this orientation often has a hydrological purpose. Researchers have noted that the sight lines of many statues point directly toward critical sources of fresh water, such as natural springs or locations where groundwater seeped to the surface. In an island environment where fresh water was a precious and sometimes scarce resource, this was a form of practical architecture. The moai, in their silent vigil, literally marked the lifeblood of the community, turning the statue into a permanent, unmissable signpost for survival. This integration of cosmology and hydrology represents the highest form of their engineering logic. It was no longer just about how to move a statue, but about where to place it and why. The process demanded a sophisticated pre-planning phase. Before a single blow was struck in the quarry, surveyors and priests likely determined the exact site based on celestial alignments and resource mapping. The entire transport route, with its pivot points and graded roads, then had to be engineered to deliver the statue to that precise spot, in the exact orientation required, so that its first sunrise view would be the correct one, and its gaze would fall upon the vital spring or the heart of the village. This transforms our understanding of the moai from isolated sculptures into interconnected nodes in a vast, island-wide network. Each statue was an anchor point in a living system that connected the heavens, the land, the water, and the people. The engineering challenge thus expanded exponentially. It was not enough to master physics, they also had to master astronomy, geography, and hydrology, synthesizing all this knowledge into a single, flawless execution. The final act of setting the statue upright on its ahu was the culmination of this grand plan, a moment when the practical and the spiritual locked together as perfectly as the stones in the platform itself. The silent giant was now awake, aligned with the cycles of the universe and the needs of its descendants, a permanent bridge between the earth and the sky. The fallen moai speak to the risks of the journey, but the scattered remnants of another resource tell a deeper story about the island's capacity. For generations, the dominant explanation for Easter Island's mystery was a tragic tale of self-destruction, a civilization so obsessed with statue building that it cut down every last tree to make rollers and sledges, collapsing its own ecosystem. This narrative of ecocide is powerful and cautionary, but modern archaeology paints a far more complex and interesting picture. The engineering logic we have followed so far, of collaboration with physics and meticulous planning, extends decisively into how the Rapa Nui managed their most vital living materials. The island was once forested with a now extinct species of giant palm tree, a towering species perfect for providing long, straight timber. It is almost certain these trees were used, their trunks cut into sections for rollers and their wood shaped into the long levers needed for the final raising. But the idea that this use was blindly destructive ignores the sophistication we have already witnessed in their stonework and transport. These were master planners who thought in generations. Evidence suggests they likely practiced techniques like coppicing, where trees are cut in a way that encourages them to regrow multiple new shoots from the stump, creating a sustainable supply of poles and timber over decades. This is not the logic of reckless consumption, but of calculated, renewable harvest. The resource management puzzle extends beyond timber. The classic image of hundreds of log rollers stretching ahead of a statue requires an immense amount of wood. But what if the system was leaner? Researchers now point to the possibility of using far fewer rollers, constantly recycling them from the back of the moving sledge to the front in a continuous loop. This method, demonstrated in experiments, would require a crew dedicated to the task but would slash the total timber needed by an enormous margin. It turns a sprawling, wasteful pathway into a tight, efficient operation, perfectly aligned with the island's finite resources. The ropes presented another challenge. While the giant palms could provide some fiber, the primary material for the incredibly strong cables needed to pull or rock multi-ton statues likely came from a more humble source, the tough inner bark of the hawhau tree, a shrub that still grows on the island today. This shifts the resource base from massive, slow-growing trees to smaller, more resilient plants that could be harvested sustainably. Even the lubricant for sledges, the sweet potato paste, was a product of sophisticated agriculture, not a wild resource. Every material choice reveals a pattern, a preference for renewable, manageable resources that could be integrated into the ongoing cycle of island life. The true story emerging is not one of a society engineering its own downfall, but of one engineering solutions within real and pressing constraints. They were not a population of thousands stripping the land bare, but likely a smaller, stable community that understood the limits of their island world. The statues were not the cause of collapse, but the brilliant, enduring output of a culture that mastered the art of doing more with less, turning careful resource management into the silent partner of their monumental ambition. This reframing is crucial, for it completes our understanding of their engineering logic. It was a holistic system where knowledge of stone, physics, social coordination, and ecological balance were all interwoven. They did not conquer their environment with brute force, they conversed with it, using its gifts wisely to achieve the impossible. This legacy of sustainable innovation, etched in stone and whispered in the landscape, may be their most relevant lesson for our own time. The engineering of the moai was never a finished blueprint. To stand before the silent ranks at Rapa is to witness a slow-motion evolution, a centuries-long conversation between ambition and stone. This is the eighth and perhaps most human principle of their logic, the unmistakable signature of iterative design. The earliest statues are modest in scale, with a squat, blocky form and simpler features. They are the prototypes, the first drafts in a monumental language the Rapa Nui were just beginning to write. But with each generation, the language grew more fluent. The figures became taller, more slender, and dramatically more refined. The brows grew more pronounced, the noses longer and more elegant, the hands and fingers carved with delicate detail that earlier versions only suggested. This progression is not random artistic drift. It is the visible record of a continuous research and development project spanning hundreds of years. Each new statue was an experiment built upon the accumulated knowledge of all those that came before. A master carver would have learned from his teachers, who learned from theirs, about exactly how deep to carve an eye socket before the tuff might fracture, or how to shape the curve of the back to better manage its center of gravity during the walk. A transport chief would have inherited stories, perhaps cautionary tales, about which slopes were too steep or which pivot points needed more preparation. Every fallen giant along a road was a costly but invaluable lesson in physics, its failure analyzed and its cause woven into the oral tradition to prevent the same mistake twice. This process of trial, observation, and refinement is the engine of all engineering. The Rapa Nui were not following a static set of instructions handed down from the start. They were writing the manual themselves, one generation at a time, through relentless, hands-on practice. The increasing grandeur of the statues is a testament to growing confidence, a culture mastering its craft through patient, incremental improvement. The final, majestic moai that gaze from the coastal platforms are not the beginning of the story. They are the magnificent conclusion of a very long, very deliberate conversation between a people and the limits of what they believed was possible. The quarry was not a silent workshop. Amidst the dust and the rhythmic labor, a hidden layer of engineering logic unfolded through sound. The very act of carving, with countless basalt picks striking the soft volcanic tuff, would have filled the bowl of Rapa with a constant, percussive symphony. This was not mere noise, but a functional soundscape, a vital tool woven into the process of creation. The crater's natural acoustics likely transformed it into a giant, open-air auditorium. The curved walls and dense rock could have amplified and carried the distinct taps and chips of work crews scattered across its slopes. A master foreman, standing at a vantage point, might not have been able to see every team, but he could hear them. The rhythm of their strikes, their pace, even a sudden silence would have carried vital information across the distance. A specific pattern of strikes might have signaled a break, a change in shift, or an alert that a team had encountered a problem. This use of sound as a long-distance communication system eliminated the need for messengers to scramble up and down the steep slopes, saving precious time and energy. It turned the mountain itself into a network where the medium of communication was the work itself, but the sound had an even more intimate purpose. When a carver's toki struck the tuff at the right angle on good, solid stone, it would produce a clear, high-pitched ring. Striking a hidden flaw, a crack, or an area of inconsistent density, however, would yield a dull, flat thud. Experienced artisans would have learned to listen to the stone as intently as they looked at it. This acoustic feedback was a form of real-time, non-destructive testing. By reading the ring of the rock, a carver could map the internal structure of the statue taking shape, adjusting their technique to avoid weak points that could cause a catastrophic fracture later during transport or raising. It was a dialogue between craftsman and material where sound revealed what the eyes could not see. This sensory dimension completes our picture of the quarry, not as a chaotic construction site, but as a finely tuned production environment. Every sense was engaged, sight to follow the emerging form, touch to feel the stone's texture, and hearing to ensure its integrity. The engineering logic here extended beyond levers and ropes into the very vibrations of the air, using the natural properties of the landscape to coordinate labor and guarantee quality, long before the first rope was ever tied. A statue's gaze held the power of a border. The ninth principle moves us from celestial alignment to a more grounded form of power, where the moai served as a terrestrial anchor. Beyond their spiritual role, what was the practical return on such a staggering investment of community labor and resources? One compelling theory frames the moai and their massive ahu platforms as monumental territorial markers, the ultimate statement of ownership etched in stone. In this view, the engineering logic is fundamentally geopolitical. The island's landscape was divided among different kin groups or clans, each needing to assert its claim to the most vital resources, the best fishing coves, the most productive gardens, and above all, the precious freshwater springs. A simple wooden post could be moved or burned. A spoken claim could be forgotten or disputed, but a 70-ton ancestor staring inland from an immovable stone platform was a declaration that could not be ignored, argued with, or erased. Its sheer physical scale was the point. The statue was a permanent, undeniable manifestation of a clan's presence, its historical authority, and its unshakable right to that specific piece of land. The statue did not just mark a resource, it became the resource's guardian and its legal document. The engineering feat itself was the core of the message. The ability to mobilize hundreds of people for years, to master the complex physics of transport, and to successfully raise the giant was a very public demonstration of a clan's social cohesion, its collective wealth in labor and food surplus, and its sophisticated organizational skill. It proved that this group was strong, unified, and capable of monumental undertakings. In a world without written deeds or fences, the moai was the ultimate property line. A rival clan looking at a towering, newly erected statue on the coast would understand the message immediately. This land, and everything within the statue's line of sight, was spoken for. The investment in stone was an investment in lasting security and legacy, a way to cement a clan's place in the island's geography for generations to come. This transforms our understanding of the statues from isolated religious icons into active participants in a social and political system, their silent faces projecting a quiet, formidable power across the valleys and shores. Theories about moving the moai are compelling on paper, but stone and rope do not read. To know what truly worked, you have to get your hands dirty. This is where modern experimental archaeology enters the story, a field dedicated to testing ancient engineering not with equations but with full-scale physical replicas. The journey to understand the moai has been propelled by daring, hands-on experiments that force abstract theories to confront the stubborn reality of weight, friction, and human endurance. One of the earliest and most famous attempts was led by the adventurer Thor Heyerdahl in the 1950s. His team, relying on the then dominant idea of log rollers, attempted to drag a concrete replica using a wooden sledge. The effort was immense, requiring large teams and a great deal of timber, and it seemed to support the idea of a slow, grinding pull. Yet it also highlighted the practical difficulties, the constant need to reposition rollers, and the sheer friction that had to be overcome. While his methods are debated today, Heyerdahl's experiment was crucial. It moved the discussion out of textbooks and into the physical world, proving that moving such masses was a problem of applied physics, not myth. Decades later, a more scientific approach took over. In 2012, archaeologists Terry Hunt and Carl Lipo, along with a team and a concrete moai replica, tested their revolutionary walking theory. They attached 2 strong ropes to their statue, and with a crew of just 18 people using a rhythmic, coordinated pull, they made the giant rock forward, pivot on its curved belly, and take a step. It worked. The experiment was filmed, and the world watched as a multi-ton figure swayed upright across the landscape. This test answered critical practical questions. It demonstrated that the method required far fewer people than previously imagined. It showed how the statue's own design, that low center of gravity and rounded base, made the motion stable and controllable. The team also learned where ropes needed to be positioned to avoid damaging the statue's features, and how different soil conditions affected the pivot. Each stumble in the experiment was a data point, each successful step a confirmation of an elegant principle. These modern experiments do more than prove feasibility, they recreate the ancient empirical process. Just as the original Rapa Nui builders learned through trial and observation over generations, modern researchers learn by doing. An idea that looks perfect in a computer model might fail when a real rope snaps under strain or when a replica digs into soft earth. Testing with replicas rules out methods that are theoretically possible but practically untenable, narrowing the field to the solutions that actually work with human hands and simple tools. This experiential bridge between theory and reality is perhaps the closest we can come to walking alongside those ancient engineers, feeling the strain in the ropes and hearing the deep groan of stone meeting earth, rediscovering their logic one careful, rocking step at a time. The final moai to stand on its hour, who did not know it was the last. When European ships first appeared on the horizon in the early 1700s, the era of the walking giants had already passed. The sight that greeted the explorers was not of a society in frenzied construction, but of a landscape where the great statues stood silent, some already lying toppled. For a long time, this moment was interpreted as an ending, a collapse of the very culture that had built such wonders. But to see it only as an end is to misunderstand the final, and perhaps most profound, principle of their engineering logic, the principle of adaptation. The systems we have explored, the quarry techniques, the walking method, the social coordination, were all brilliant solutions to a specific set of challenges within a specific time. They were not a permanent state, but a dynamic response. When the societal and environmental context of the island shifted, as all contexts inevitably do, the engineering logic did not simply vanish. It pivoted. The monumental energy of the Rapa Nui did not dissipate, it was redirected. Archaeologists note a fascinating transition in the archaeological record. The carving of new moai from Rano Raraku ceased, but the work on the sacred Ahu platforms continued and even intensified. communities began to modify existing altars, rebuilding and reinforcing them. Their focus turned inward toward new forms of ceremonial architecture and stonework that served the needs of a changing world. They began constructing what are known as hairpinga, or boat-shaped houses, with meticulously fitted stone foundations that show the same mastery of dry stone masonry once reserved for the Ahu. This shift tells a powerful story. It teaches us that engineering is never an end in itself. It is a tool for living. The logic that moved 70-ton statues was not about the statues. It was about solving problems of transport, balance, and collective purpose. When the cultural imperative to erect new ancestral giants faded, that same problem-solving intelligence was applied to new challenges, perhaps challenges of community cohesion, territorial defense, or adapting to new social structures. The end of moai construction was not a failure of ingenuity, but its ultimate validation. It proves that their greatest creation was not the stone figures, but the adaptable, resilient mind that conceived them. A system that cannot change when the world changes is not a smart system, it is a brittle one. The Rapa Nui, by redirecting their efforts, demonstrated that the true legacy of their engineering was not frozen in tuff, but lived on in the continuous, creative application of knowledge to the pressing needs of the present. Stone was not just for giants. While the moai command the horizon, a quieter, more intimate form of engineering was at work at ground level, nurturing the very life of the island. Recent archaeological discoveries have peeled back the grassy surface to reveal a hidden landscape of astonishing sophistication, a testament to the Rapa Nui as masters of hydrological and agricultural engineering. This is the unseen logic that sustained the society behind the statues. Scattered across the island are vast, strange fields littered with thousands of fist-sized volcanic rocks. To the untrained eye, they look like barren wastelands, but to a farmer centuries ago, this was a lush, productive garden. This technique is called Lithic mulching, and its genius is in its simplicity. By covering the soil with a dense layer of broken basalt stones, the Rapa Nui solved multiple critical problems at once. The stone blanket acted as a shield against the strong, drying winds that sweep across the island, drastically reducing evaporation. It moderated soil temperature, keeping roots cooler under the harsh sun and warmer during cool nights. As dew condensed on the cool stones at night, it would trickle down to the soil below, providing a nightly, gentle irrigation. Over time, the stones themselves would slowly weather, releasing essential minerals and nutrients directly into the earth. This was not haphazard rock dumping. It was a deliberate, calculated system of soil enhancement. It transformed marginal land into fertile, moisture-retaining plots capable of supporting vital crops like sweet potatoes, taro, and yams. The logic is one of amplification, using the island's most abundant material, stone, to multiply the effectiveness of its most precious resource, water. But their water management extended far beyond the garden plot. In an island environment with no permanent rivers and porous volcanic rock, capturing and directing every drop of fresh water was a science. The Rapa Nui engineered intricate systems to intercept the water table. They lined natural springs with precisely fitted stonework, creating protected catchment basins. They dug deep, stone-reinforced wells to tap into subsurface flows. Perhaps most impressively, they sculpted the land itself to channel rainwater. Archaeologists have found evidence of subtle terracing and networks of stone-lined channels designed to capture runoff from slopes and direct it toward cultivated areas or storage pits. This hydraulic engineering required the same precise observation and patient labor as moving a statue. It demanded an intimate understanding of the land's contours, the flow of water, and the behavior of materials. A channel had to be graded just right. Too steep and the water would erode it, too shallow and it would stagnate. A well stone lining had to be fitted to prevent collapse while allowing seepage. This small-scale engineering provides the crucial, missing context for the moai. It shows a society that did not merely conquer its environment with monumental acts, but conversed with it through daily, nuanced manipulation. The same community that could orchestrate the rhythmic walking of a 70-ton giant could also spend patient hours placing stones in a field to coax moisture from the air. The monumental and the mundane were not separate endeavors, they were two expressions of the same innovative mind. The logic that moved mountains of stone was fundamentally the logic that carefully nurtured the soil and water needed to feed the people moving those stones. This reveals the true foundation of their society, built not on reckless expenditure, but on a deep, sustainable partnership with a fragile island world. The silent giants of Rapa Nui speak a language of physics understood across the ancient world. When we place their story beside other monumental achievements, a remarkable pattern emerges. Isolated cultures, separated by vast oceans and thousands of years, repeatedly converged on the same handful of brilliant solutions to move the immovable. This comparative logic reveals that the engineering behind the moai was not a singular miracle, but part of a universal human dialogue with stone. Consider the blue stones of Stonehenge, transported over 150 miles from the Preseli Hills in Wales. While the exact method remains debated, the leading theories are hauntingly familiar. Archaeologists propose the Neolithic builders may have used a combination of wooden sledges and a track of greased logs, a system of rollers and lubrication that mirrors the sweet potato-lubricated tracks hypothesized for Easter Island. The core challenge was identical, reducing friction to make multi-ton stones glide. Half a world away, in the lush mountains of Colombia, the San Agustin culture carved hundreds of monolithic statues eerily reminiscent of the moai, with stern faces and upright postures. Though smaller, moving these figures through rugged terrain would have demanded the same principles of leverage, rocking, and controlled descent. The solutions were born not from shared blueprints, but from shared constraints. The ancient Egyptians, masters of obelisk erection, provide perhaps the most detailed parallel. To raise a 100-ton stone needle, they constructed massive earthen ramps, used levers and packed fill to incrementally lift the monolith, and likely employed water or mud as a lubricant on the incline. This patient lift and pack technique is virtually identical to the method proposed for raising the moai onto their Ahu platforms. The convergence is stunning. Different minds across different epochs looked at a massive stone and asked the same question. They then independently discovered that the answer lay not in mythical strength, but in manipulating a few key variables: friction, leverage, center of gravity, and incline. This points to a profound truth. When confronted with the fundamental physics of mass and friction, a universal engineering logic naturally emerges from human ingenuity. It is a logic of working with the environment, not against it, of breaking impossible tasks into a sequence of possible steps. The Rapa Nui did not need contact with Egypt to understand the power of a ramp, any more than a child needs instruction to use a lever to pry up a rock. These principles are latent in the material world, waiting to be discovered by any culture determined enough to try. This shared legacy transforms the moai from an isolated wonder into a powerful testament to a collective human heritage of problem-solving. It suggests that our ancestors, wherever they were, possessed a common toolkit of the mind, an intuitive grasp of mechanics that allowed them to reshape their world in stone. A computer screen now illuminates the ancient mystery. Modern engineers have a powerful new tool to interrogate the past, not with shovels but with algorithms. They employ a technique called finite element analysis, a computational method that digitally dissects a complex object into millions of tiny, simple pieces. By applying the laws of physics to this virtual mesh, they can model exactly how forces travel through a material, revealing hidden points of strain and stress that would be invisible to the naked eye. For the moai, this is a revolution in understanding. We can now load a precise digital model of a statue with virtual ropes, place it on a simulated slope, and apply pulling forces from any direction. The software calculates in exquisite detail what happens inside the stone. Where would cracks most likely begin if the rope angle was too steep? How does the statue's unique shape, that low center of gravity and rounded belly, actually redistribute stress during a rocking motion? These simulations allow us to test theories with a rigor that physical experiments cannot always provide. We can run the same scenario 10,000 times, altering a single variable each time, like the density of the tuff or the exact position of the pulling teams. This digital sandbox lets us fail spectacularly and safely to see all the ways a statue could have shattered in order to appreciate the one narrow path that kept it intact. The computational logic provides quantitative validation for what was once qualitative guesswork. It can tell us with mathematical certainty that a particular rocking rhythm creates a stable, oscillating force pattern, while another rhythm introduces a twisting moment that would shear the base. It can show us the optimal points on the statue's body to attach ropes to minimize surface pressure and prevent the stone from crumbling under the cables. This is not about replacing the human story with cold data, but about deepening our awe for the ancient engineer's intuitive mastery. The simulations often confirm that the methods we theorize, like the walking technique or the incremental lift, are not just possible, but are elegantly aligned with the material's physical limits. They reveal that the Rapa Nui, through generations of trial and observation, had empirically mapped the same stress landscapes that our computers now chart. The digital moai, tested to its breaking point 1,000,000 times over, stands as a silent tribute to those who first learned its limits by listening to the ring of stone on stone and the careful, collective rhythm of a community in motion. The stone giants were not just moved by society, they actively shaped it in return. This is the 11th principle, the powerful cultural feedback loop where engineering and belief became one self-reinforcing system. Each successful statue movement was far more than a technical victory. It was a profound spiritual and social event. Imagine the moment a giant was finally seated on its ahu after a journey of months. The community that had pulled the ropes, chanted the rhythms, and packed the stones would have witnessed a tangible miracle, a direct result of their collective faith, unity, and skill. This success validated their entire worldview. It proved their ancestors were pleased, their leaders were legitimate, and their gods were listening. The shared triumph reinforced social hierarchies as the chiefs or priests who organized the feat saw their authority cemented. More importantly, it solidified a powerful communal identity. They were not just a group of families, they were the people who could make the stone walk. This reinforced identity then fueled the next, even more ambitious project. The logic was never purely technical, it was socio-technical. The act of engineering was itself a sacred ritual, a ceremony that strengthened the exact social cohesion, discipline, and shared purpose required to perform the engineering in the first place. It created a virtuous cycle. A strong, unified society could undertake a monumental project, and the successful completion of that project made the society feel even stronger and more unified, eager to honor their ancestors with an even grander testament. This deep intertwining of the spiritual and the practical is what made the endeavor sustainable for centuries. The statues were not a drain on the culture, they were its engine, providing meaning, order, and a common goal that transcended generations. The project and the people were in constant dialogue, each shaping the other, building a civilization as resilient and interconnected as the stonework of their platforms. This loop continued until external forces, like new arrivals and the profound changes they brought, introduced pressures from outside the system. disrupting a cycle that had sustained a unique and brilliant way of life for hundreds of years. The wind that once guided the walking giants now works tirelessly to erase them. For centuries after the last statue was raised, the moai stood their silent vigil, locked in a slow, invisible war with the elements. Rain seeped into microscopic cracks, freezing and expanding in rare cold snaps. Salt spray from the crashing Pacific coated their porous tough skin, crystallizing and slowly crumbling the stone from within. Most devastating of all were the island's fierce storms, which over generations pushed against the monumental forms, gradually unsettling their foundations until, one by one, they toppled forward, their faces meeting the earth with a final, silent impact. This natural erosion was a process the original engineers could not have designed against, an enemy of infinite patience. By the dawn of the 20th century, not a single moai remained standing on its ahu. The great stone faces lay buried in sediment or half swallowed by the sea, their story seemingly complete. Yet this was not an ending, but the beginning of a new chapter in their engineering legacy, one written not with stone tools, but with cranes, lasers, and a deep sense of custodianship. The modern effort to resurrect the fallen giants is an engineering puzzle that directly mirrors the ancient one, but in reverse. Where the Rapa Nui sought to move and raise new creations, today's archaeologists and conservators must carefully retrieve, repair, and re-establish the old. The first major restoration project began in the 1950s, led by the same Thor Heyerdahl who had experimented with moving replicas. His team at the site of Ahu Akivi faced the monumental task of locating 7 specific moai that had tumbled from their platform, some buried under centuries of soil. Using nothing more than wooden poles, ropes, and sheer manpower, they reenacted the ancient lift and pack method in miniature, painstakingly raising each statue a few inches at a time to place temporary supports underneath, a process that took weeks for each figure. This hands-on work provided the first modern data on the statue's true weight and balance, confirming the ancient engineers' brilliance while highlighting the immense difficulty of their own task. These early restorers were pioneers, working with a reverence for the past but limited by the technology of their time, often using concrete to patch damaged stones, a method later conservators would reconsider. Today, the philosophy and technology of preservation have evolved into a sophisticated science. The goal is no longer just to make a statue stand again, but to ensure it stands for centuries more, with minimal intervention to its original material. Before a single cable is attached, teams now conduct extensive digital surveys using 3-dimensional laser scanning and photogrammetry. These technologies create a perfect, millimeter-accurate digital twin of the fallen statue and its platform. Engineers can then run countless simulations on this digital model, calculating the precise center of gravity, identifying hidden stress fractures invisible to the eye, and testing different lifting points to avoid causing new damage. It is a virtual rehearsal for a one-time performance where failure is not an option. The actual re-erection is a ballet of modern and ancient logic. Steel I-beams and hydraulic jacks might replace wooden levers, but the principle of the incremental, controlled lift remains identical. Custom-fitted slings cradle the statue's fragile form, distributing pressure evenly to prevent the stone from cracking under its own weight. The most delicate part comes at the moment of pivot, as the multi-ton mass swings from horizontal to vertical. Modern engineers, with their computer models and strain gauges, hold their breath just as the ancient rope crews must have, placing their trust in physics and preparation. The greatest threat to the moai today is not time alone, but the footsteps of those who come to admire them. Tourism is a double-edged sword, providing vital resources for conservation while simultaneously accelerating the very decay it seeks to witness. Thousands of visitors each year, however careful, bring microscopic organic matter, alter local humidity by their presence, and contribute to gradual soil compaction around the fragile sites. In response, preservationists have engineered a new kind of landscape management. At the Quarry of Rapa, viewing platforms and defined walking paths now keep visitors at a respectful distance, preventing erosion caused by wandering feet. Sensors monitor air quality and humidity around key statues, providing data to help manage visitor flow. Perhaps the most profound shift is in the materials used for repair. Gone are the days of concrete patches. Modern conservators now use a science of compatibility, developing custom mortars made from crushed local tuff, mixed with lime-based binders that match the original stone's porosity and strength, allowing the repair to breathe and weather alongside the ancient material. The logic is one of humility: to support without replacing, to strengthen without disguising. This ongoing work ensures the moai remain not just as relics but as active teachers. Every crack analyzed, every erosion pattern mapped, and every successful re-erection adds another line to the instruction manual the Rapa Nui left behind. When a conservator discovers how salt crystallization is hollowing out a statue's base from within, they gain a deeper appreciation for why the original builders chose certain stone types or orientations. When an engineer calculates the exact force needed to safely right a toppled giant, they are, in essence, retracing the steps of the ancient master who first raised it. The modern preservation effort is therefore a continuous dialogue across centuries. It is a partnership where contemporary problem-solving sheds light on ancient methods, and where the enduring challenges of these stone giants continue to inspire innovative solutions. The silent sentinels, now standing once more on their windswept platforms, are no longer static monuments to a finished past. They are dynamic participants in a living story of human ingenuity, their restored gaze challenging each new generation to learn, to preserve, and to understand the enduring logic etched in stone. The impossible has been solved. The stone giants of Easter Island are no longer a mystery, but a masterclass in applied human intellect. We have followed their journey from the soft tuff of the quarry to their eternal vigil by the sea, uncovering a logic far more impressive than any myth of alien intervention. This was not magic or lost super technology. It was the brilliant, layered engineering of a people who looked at a 70-ton block of stone and saw not an obstacle, but a partner in a grand, physical conversation. Their logic unfolded in clear, deliberate layers. It began with a deep material science, choosing and mastering a volcanic rock that was soft to carve but hardened with time. It leveraged physics in stunning ways, using the statue's own weight and curved base to make it walk, or employing sweet potato paste to defeat friction on a track. It relied on patient, generational iteration, where each new moai was a refined prototype built upon the lessons and even the failures of the last. And above all, it was powered by an immense social cohesion, the living engine of hundreds of voices moving as one to a shared rhythm. Their story dismantles the old, tragic narrative of a people doomed by their own ambition. Instead, we see a society of resilient innovators who worked within their island's constraints, using sustainable practices and renewable resources to achieve the extraordinary. They were not conquered by their environment, they collaborated with it, turning careful observation into monumental achievement. This reframing is their most vital legacy. The moai stand as a powerful reminder that true innovation is not about the resources you lack, but the ingenuity you apply. It flourishes in isolation, under pressure, and in the shared purpose of a community. When we look at these silent faces now, we should see not a cryptic puzzle, but a familiar brilliance. We see the universal human drive to solve, to build, and to leave a mark that whispers across centuries. It is a story written in the language of levers, ropes, and balanced stone, a story that belongs not to a lost world, but to all of us. If this journey into ancient logic captivated you, consider subscribing for more deep dives into history's greatest puzzles. Let us know in the comments which other megalithic marvel you would like to explore next.